Spacetime Cafe, welcome, Ubiquity.
Ever notice how in math there's this almost like a hidden beauty when you find something that just brings order to what seems like total chaos?
Yeah.
It's like you find this underlying rule and it just makes everything click right.
Absolutely. And mathematicians, we have a name for these kind of rules. We call them invariants. Think of it as like a fixed point that never changes no matter what kind of crazy transformations are happening around it.
And for someone like me, always trying to find those shortcuts to knowledge to really grasp something quickly, those invariants are pure gold. Once you get them, it's like having a cheat code for problem solving. You know what I mean?
Totally. And that's precisely what makes this deep dive so fascinating.
All right, so what are we diving into this time?
We're going to tackle this problem. They call it the fraction matrix problem.
Okay, the fraction matrix problem. That does sound a little intimidating, I got to admit.
Yeah, the name's a bit much, but trust me, what's really cool is how we can use a simple mathematical invariant to solve this thing efficiently.
Okay, I'm intrigued. Lay it on me. What is this problem all about?
At its heart, we're trying to find the k smallest fraction out of a huge set of fractions.
A huge set, okay.
Yeah, and these fractions, they're not just any random fractions. They're formed in a very specific way. You've got numerators that come from a given list, and then the denominators, they're derived from prime numbers raised to certain powers, and then you subtract one. It's a whole thing.
Prime numbers, powers minus 1. Okay,
Yep.
and then we're supposed to find like the 10th smallest or the 100th smallest out of all these things?
Exactly. You got it. And there's another twist. We have to consider these fractions after they've been rounded to a certain precision level, like to a certain number of bits.
All right, so not only do we have this crazy way of making fractions, we're also rounding them, so it's getting even more complex.
Yeah. And here's where it gets really mind-boggling. The number of possible fractions we could end up with can be absolutely massive. I'm talking like on the order of 10 to the 11th power, or even bigger, depending on the problem's limits.
10 to the 11th, that's like trying to count all the grains of sand on a beach or something.
It's a huge number, and if you tried to actually create all those fractions and then sort them to find the kth smallest one, good luck, your computer would probably just give up.
It would overheat or something, yeah.
Basically, so that's where our invariant comes in.
All right, so that's what we're here to uncover today. How do we use this invariant to solve this seemingly impossible fraction problem?
Exactly. We're going to break it down step by step. So by the end of this, you'll have that aha moment about the power of invariance in algorithm design.
Love those aha moments.
All right.
Let's crack this thing open.
So the invariant at the heart of this solution, it all comes down to something called a counting function.
A counting function.
Yeah.
It's pretty basic.
It is in a way, but it's the way we use it that's clever.
Yep.
So let's say we have this function. We'll call it ffx.
All right.
Go on.
And this function tells us how many of our special fractions, those ones with the primes and the powers and all that, are less than or equal to a specific value after we round them to that b-bit precision we talked about.
Okay, so our fraction counter for any number, it tells us how many of our fractions are smaller than or equal to. Got it. But how does this help us find the kf smallest one?
Yep. The key is that this is a very special property. It's what we call monotonic non-decreasing.
Monotonic non-decreasing. Okay, you're going to have to break that down for me.
Fair enough. What it means is that as the value of gets bigger, the number of fractions that are less than or equal to can only increase or stay the same. It can never go down.
So it's like climbing a hill. You can go up or stay at the same level, but you can never suddenly drop down. Exactly a perfect analogy. So if you raise that bar, you're not going to suddenly have fewer fractions falling under it. You might have more or the same amount, but never less.
That makes sense. But why is this always true for our fraction problem? What's the math behind it that guarantees this monotonic thing?
Good question. Let's imagine we have two thresholds by 1 and by 2, where pi 1 is smaller than by 2. Now remember how we form those fractions. We have a numerator pran from our nums array and a denominator that looks like pj1, where it's from our primes, and j is within a certain range.
Yep, I'm following so far.
So for a fraction to be less than or equal to our threshold, it has to satisfy this inequality, npj1.
Okay, yeah, that makes sense.
Now if we bump up our threshold from by 1 to by 2, the right side of that inequality, CJ1, gets bigger too, right?
Right, because we're multiplying by a bigger number.
Exactly. And since our numerators in the nums array are fixed, a larger target value on that right side might let more values satisfy the inequality. It can't allow fewer. And when we do this for all the possible denominators and add up all those counts, that's why our counting function is always non-decreasing.
So basically by increasing, we're like widening a net to catch those fractions, and we might catch more, but we'll never lose the ones we've already caught. I like that analogy.
Perfect. That's the intuition.
Yep.
So we have this counting function that behaves predictably in one direction only. And now the question is, how do we use this to actually find that k⁻³ smallest fraction efficiently?
Yeah. How do we actually put this into action?
This is where the magic of binary search comes in.
Binary search. I remember that from my intro to computer science, but how does that apply to this crazy fraction problem?
Because it's monotonic, it gives us a powerful way to search. Think about it. If we pick a value and calculate, and we find that it's less than k, what does that tell us?
It means we haven't found enough fractions yet that are smaller than or equal to x to reach our target of k.
Exactly. So we know for sure that the k⁻³ smallest fraction has to be bigger than this we picked. There's no way it could be smaller because we haven't even counted fractions up to that point.
Makes sense. So we got to aim higher.
Exactly. And on the flip side, if we find that f(x) is greater than or equal to k, then we know we've overshot it. The k⁻³ smallest fraction must be less than or equal to this, f(x), because we've already found at least k fractions in that range.
So basically, we're using fx to zero in on where the k⁻³ smallest fraction must be. We're constantly narrowing down the possibilities.
Precisely. And the beauty of binary search is that it's super efficient. With each step, we cut our search space in half.
It's that classic guessing game where you say a number and someone tells you higher or lower.
Yeah, exactly like that. But with the added bonus that our answer, that k⁻³ smallest fraction, always moves in a predictable way based on our guesses, and that predictability comes directly from the monotonic nature of f's.
So every guess we make gets us closer to the answer, and we know which way to adjust our next guess based on whether it's too low or too high.
Exactly, and that's why binary search is so powerful. It leverages this invariant, this monotonic property, to make the search incredibly fast, much faster than if we had to check every single fraction individually.
It's all about efficiency, finding the answer with the fewest possible steps.
Now, let's actually walk through how this binary search would work in practice.
Yeah, let's get into the nitty-gritty.
So first off, we need to set up our initial search space. What do you think would be a reasonable starting range for the value of the k⁻³ smallest fraction?
We know all the numerators and denominators are positive, so all of the fractions will be positive too.
Right.
And since we're dealing with ratios and rounding them to a certain precision, it's probably safe to assume the answer is going to be somewhere between 0 and 1 inclusive.
Exactly. That's a great starting point. So we begin our binary search with a lower bound, we'll call it low, set to 0, and an upper bound high set to 1. This interval from 0 to 1, it's guaranteed to contain our k smallest fraction.
Okay, so we have our starting range now. How do we know when to stop searching? We can't keep going forever, right?
We need a stopping condition, and that's where that b-bit precision comes into play. We keep going with our binary search until the difference between high and low is less than 1 2b.
Okay, so once our upper and lower bounds are super close together, essentially indistinguishable at that b-bit precision, then we're good to go.
Exactly. At that point, any value within that tiny remaining interval, when we round it to bits, it's going to give us the same result. We've essentially narrowed it down as far as our required precision allows us.
So what happens inside each step of this binary search loop? What's the main operation?
So inside the loop first, we find the midpoint of our current interval, the one between low and high. We can call that mid, and it's just the average of the two.
Okay. Simple enough. Find the middle.
And once we have that mid value, we use our handy counting function. This tells us how many of our generated fractions, after rounding, are less than or equal to this mid value.
Okay, so we're using fx to see how many fractions fall below our midpoint. And then what?
Then, based on that count, we adjust our search window, our low and high boundaries. If f is less than, what does that tell us?
It means we need to look at bigger values because we haven't hit our target of k fractions yet.
Right on. So we update our lower bound. We set low to be equal to mid. We're basically tossing out the entire lower half of our search interval because we know the answer's got to be somewhere above it.
And if f is greater than or equal to k, then we do the opposite. We move our upper bound down to mid because we've already found at least k fractions below or equal to that point.
Precisely, we're constantly narrowing down the range where the kth smallest fraction must be hiding, and we're guaranteed to be making progress with each step thanks to that monotonic behavior of x.
So it's all about this interplay between the binary search and our counting function.
Yeah.
It's guided by this invariant, this monotonic property.
Exactly. And to really appreciate how elegant this solution is, remember that we're never actually generating and sorting their entire massive set of fractions explicitly.
Right, it's like we're searching through a giant library without having to pull every book off the shelf.
Yeah, it's a form of compression at a conceptual level.
Yep.
We're querying the data as if it were all there without having to store it all.
It's like we have a map of the library,
Mm.
and we can just pinpoint the exact location of the book we need without having to look at every single one.
Exactly. And this idea of using a monotonic counting function along with binary search, it's not just limited to fractions either.
Oh, really?
Yeah, this approach can be applied to any situation where you have a structured set of elements, a clear way to order them, and most importantly, a monotonic counting function that tells you how many elements are below a certain value. Imagine you want to find the k smallest sum of pairs from two sorted arrays. If you can efficiently count how many pairs have a sum less than or equal to a given target, you can use a similar binary search strategy.
So it's a more general principle that can be applied to all sorts of problems.
Exactly. The key is that monotonic counting function. It's like a secret weapon for efficient searching. It lets you quickly navigate through a potentially massive space of possibilities.
So we've tackled this problem without actually going insane ourselves.
And we did it by understanding and exploiting this invariant, this simple yet powerful property of our counting function.
I gotta say, these invariants, they're pretty amazing once you see how they work.
It's like we're talking about the hidden architecture of complex systems, and grasping the concept of invariance is like finding the secret blueprint, the master key that unlocks their inner workings.
I'm starting to see how this could be a powerful framework.
Oh, it absolutely is. And what's super cool is that it lets us make these wild connections between fields that seem totally unrelated at first.
Like what kind of connections?
Buckle up, because we're going to see how the sheer difficulty of untangling certain knots could be the key to keeping your online data safe from prying eyes.
Knots and cybersecurity.
The wonderfully twisted world of knot theory.
Okay, knots. I think I can tie my shoelaces, so I'm already ahead of the game.
Knot theory goes way beyond shoelaces. But hey, those are a great example of everyday knots. Now, for anyone who hasn't pondered the mysteries of knotted headphones, and seriously who hasn't been there, knot theory is basically the math behind these tangled loops we see everywhere, especially in 3D space.
It's not just about untying them, though I admit I'm pretty good at that too.
I bet you are. But knot theory digs much deeper. It's intimately connected to this fascinating field called topology. Think of topology as the study of shapes and their properties that just don't quit, even when you're stretching, twisting, bending them every which way.
As long as you don't rip them apart or anything.
Exactly. No cutting or tearing allowed. And this idea of things staying the same, that's our old friend invariance, is absolutely at the core of topology, wouldn't you say?
Absolutely. It's all about what properties remain unchanged under these transformations.
Yeah.
Like a donut and a coffee cup are topologically equivalent because you can deform one into the other without any cutting or gluing.
It's like they have the same underlying dough-like essence. Okay, so back to knots. In knot theory, we search for what we call knot invariants. These are like special properties or quantities that stick with a knot no matter how much you wiggle, reshape it, as long as you follow the rules, no cutting or passing it through itself.
So like a unique fingerprint for each type of knot, no matter how tangled it gets.
You got it. It's like a secret code that reveals the knot's true identity. Now, you might be wondering, what does this abstract knot fingerprint have to do with keeping my online shopping spree safe and sound?
Yeah, that was my next question.
Okay.
Seems like a big jump from knots to like credit card security.
Yeah, it does. But here's where it gets super cool. There's this concept called the hardness of knot equivalence. It basically means that from a computer's perspective, it's incredibly challenging, mind-bendingly hard to figure out if two given knots are actually the same.
Even if they look completely different.
Exactly. They might look wildly different, all tangled up in different ways, but they could actually be the same knot at their core, topologically speaking, meaning you could morph one into the other without any sneaky cuts or breaks. So it's a bit like those spot the difference games, where you're staring at two pictures that seem identical, but there's one tiny detail that sets them apart. Except here, the difference is hidden within the complex topology of the knot itself.
And I'm guessing it's way harder than those games.
Oh, exponentially harder. Computers can sweat over this for ages. And the only surefire way to prove two knots are the same is by going through a series of specific fundamental moves called Reidemeister moves. Think of these as the rule book, the allowed moves you can make on a knotted string without resorting to scissors or any magic tricks.
Like sliding one part of the string over another in a particular way.
Exactly. And these moves don't change the knot's fundamental knottiness, its essence. But the catch is finding the right sequence of these moves to transform one knot into another. That can be a real head-scratcher, even for supercomputers. It's like a cosmic-level Sudoku puzzle.
Oh, I see where this is going. If it's that hard to tell if two knots are the same, that very difficulty could be used to create a virtually unbreakable code.
You're catching on quickly. That's the beauty of it. This computational nightmare of knot equivalence can be transformed into a trapdoor function, a core concept in cryptography. It's like a one-way street. It's easy to go in one direction, take a simple knot, and make it look incredibly complex through a series of these Riedemeister moves. But to go back, to untangle that mess and figure out the original simple knot, good luck with that without knowing the exact steps that were taken.
It's like scrambling an egg. Easy to do, but good luck trying to unscramble it. So how would a cryptographic system built on knots actually work?
All right, imagine this. You start with a simple base knot. Think something like a torus knot, which looks a bit like a donut, or the classic figure-8 knot. This base knot is your secret, your private key. Got it.
Okay, the simple knot is the private key, kept under wraps.
Then you let loose. You apply a long, convoluted series of these Riedemeister moves and other topological twists and turns to that simple knot. You basically make it look as ridiculously complex as possible, and that transformed knot, that's your public key, the one you can share freely.
So the public key is like this insanely tangled mess that anyone can see, but only the person with the private key, the original simple knot, and the knowledge of how it was transformed can untangle it.
You're getting the hang of this. Now, to send you a secret message, someone would encode their message into a transformation of your public key. They might use something like a braid representation of the knot where you visualize it as interwoven strands. The message would then tweak this braid in a specific way, and bam, you have your encrypted message disguised as a tweaked, complex knot.
And only someone with the private key, the original knot, and the sequence of transformations can reverse the process and decipher the message hidden within that knotty mess.
You nailed it. Anyone else trying to crack the code would be faced with this computationally impossible task of trying to figure out if that public knot, that tangled monstrosity, can be simplified back to any possible base knot. It'd be like trying to solve a Rubik's Cube with a blindfold on in the dark while riding a roller coaster.
Talk about a headache. But what makes this kind of encryption truly secure? Like, how does it stack up against the traditional ways we protect our data?
That's a great question. The security comes from a few key features that are baked into the very nature of these knot invariants and that pesky hardness of knot equivalence. First off, as we've discussed, you've got that one-way street situation. Easy to complexify, practically impossible to simplify without knowing the exact route taken. Secondly, it introduces a whole different kind of kryptonite for hackers. Most encryption today relies on problems in number theory, like the headache of factoring huge prime numbers, finding those two numbers that multiply together to give you a giant number.
Prime numbers, those numbers that are only divisible by 1 and themselves, they're notoriously difficult to deal with, especially when they get massive.
Exactly. But knot theory brings topological hardness to the table. It's a completely different mathematical beast, a whole new foundation for security. And this is where it gets really interesting, especially with the rise of quantum computers.
Quantum computers, those super powerful machines that everyone's talking about, what do they have to do with knots?
Quantum computers, at least in theory, could blow traditional encryption out of the water. They could run algorithms like Shor's algorithm, which could factor those massive numbers in a snap, cracking current encryption schemes wide open.
So all our online secrets would be spilled.
Potentially, yes. But here's the good news for our naughty friends. Right now, there's no known quantum algorithm that can efficiently tackle the general knot equivalence problem. So if these knots can withstand the quantum onslaught, they could be our digital guardian angels in a post-quantum world.
So these tangled loops might be our best bet against quantum hackers. That's both amazing and terrifying.
It is, isn't it? It really highlights the power of looking beyond traditional approaches. A nightmare for hackers, but a dream for cryptographers.
One big one is computational complexity. We've said that the general problem of telling if two knots are the same is hard, but not all knots are created equal. Some are trickier than others. So for cryptography to really work, we need to choose base knots and transformations that are provably hard to reverse, even with all the computing power in the world.
So finding the right knots for the job is crucial. What else?
Another hurdle is that, unlike the neat binary world of computers where everything's ones and zeros, there's no universal way to represent knots digitally. And this lack of standardization could make actually using knot-based cryptography more complicated.
So some kinks to iron out, so to speak.
Exactly. But the potential is huge.
And as you mentioned earlier, the invariants themselves, things like the Jones polynomial, the Alexander polynomial, and fundamental group of a knot, could actually be the secret keys.
That's right. They're like the hidden codes embedded within the knots themselves.
Okay, let's shift gears from the world of physical knots to something equally fascinating. Recognizing invariance isn't just a math or physics thing, it's a fundamental part of being intelligent, whether you're talking about the human brain or a sophisticated AI. This idea that the ability to spot what stays the same, even when everything around is changing, that this is a defining characteristic of intelligence. But that's not exactly mainstream thinking, is it?
You're right. It's still a fairly radical idea. While most people agree that intelligence involves recognizing patterns and regularities, the notion of this unified meta-invariant framework, where this ability to detect and apply invariance is seen as the defining characteristic of intelligence across all domains, that's a bit more out there.
So it's like a new lens through which to view intelligence, a new way of understanding what it means to be smart. But even if it's not mainstream yet, are there any ideas out there that kind of hint at this meta-invariant concept, even if they don't explicitly use that term?
Definitely. Like in cognitive science and neuroscience, you see it in things like perceptual constancy. It's our brain's superpower. It can perceive objects as stable and unchanging even when the sensory information we're getting is all over the place.
If you're looking at a door, it still looks like a rectangle, even when you're looking at it from a weird angle.
Exactly. Our brains are picking out the door's invariant features, its true shape, even though the perspective is shifting. It's like our brains are constantly saying, okay, the image on my retina is changing, but the door is still a door. It's not morphing into something else. And then there's the whole process of concept formation, where we learn to generalize from specific instances that relies on us recognizing the invariant relationships between things, the core features that define a concept, regardless of the specific examples we encounter.
So learning that a dog is a furry, four-legged creature, even though there's so many different breeds of dogs.
Precisely. Things like Friston's free energy principle, where the brain is constantly trying to predict incoming sensory information. That relies heavily on building models of the world that focus on the stable, unchanging aspects, those invariant features. In AI, recognizing invariance is key to making progress. Take convolutional neural networks, or CNNs, for instance. They've revolutionized image recognition. And they do it by recognizing spatial invariance, the features of an object that stay the same, even if the object moves or rotates within an image.
So they can identify a cat whether it's sitting, lying down, or doing a backflip.
Exactly. The cat's position and orientation might change, but the essential catness remains invariant. And then there are the transformer models that are all the rage in natural language processing. They use these clever self-attention mechanisms to extract higher-order representations of meaning from text. And these representations are designed to be stable and unchanging even when the sentence structure or word order changes.
So it's about finding the meaning that stays constant even when the way it's expressed varies.
Exactly. And when we talk about the goal of generalization in AI, the ability for a model to apply what it's learned to new, unseen data, that fundamentally depends on the model's ability to learn and utilize these invariant features. Physics and mathematics are full of examples, too.
Physics and math. Okay, I'm all ears.
Noether's theorem. It establishes this profound link between symmetries and the laws of physics and the existence of conserved quantities.
Okay, and how does symmetry tie into this?
Symmetry itself is a form of invariance. For instance, the laws of physics don't care where you are in space or when you are in time, they stay the same. That's symmetry. And Noether's theorem tells us that these symmetries directly lead to the existence of these conserved quantities. So the invariance of the laws of physics under certain transformations is directly tied to these quantities that are also invariant.
So the fact that physics works the same way everywhere and at all times leads to the conservation of energy and other fundamental quantities. It's like the universe is built on a foundation of invariance.
It really is. And even in mathematics, especially in topology, as we saw with knot theory, the whole point is to study the properties of shapes and spaces that remain invariant under these continuous transformations. And in statistical mechanics, you see these stable statistical properties emerging from systems that, at the individual level, seem totally chaotic.
So We keep coming back to this idea that intelligence, whether it's biological, artificial, or even reflected in the laws of the universe, seems to be deeply intertwined with this ability to recognize and utilize invariants. You mentioned that this meta-invariant concept, this idea that recognizing invariance is the defining feature of intelligence, it's not exactly widely accepted. What makes it so different or novel?
It's about bringing all these different fields together and saying, hey, there's this fundamental ability here that connects them all. It's about elevating this idea of recognizing invariance from being just an important tool within specific disciplines to being the core principle of intelligence itself.
It's like saying that the ability to find those unchanging fundamental truths is the essence of what it means to understand and learn.
Oh, absolutely. You can see echoes of this idea in various fields, like philosophers like Douglas Hofstadter and Jerry Fodor. They talk about conceptual invariance in human reasoning, how we can recognize the same underlying concept even when it's presented in totally different ways. And in AI, researchers are always talking about building models that show feature invariance to make them more robust and adaptable. Neuroscientists studying things like perceptual constancies in predictive coding are also essentially exploring how the brain extracts and uses invariant features. But what sets the meta-invariant concept apart is that it's not just about observing this phenomenon within specific disciplines. It's about proposing it as a unifying theory of intelligence across all domains.
What could it mean for us? What kind of impact could it have?
The implications could be huge, like for artificial general intelligence or AGI, the quest to create machines that are genuinely intelligent. It could mean shifting the focus from just getting AI to ace specific tasks to building systems that are inherently good at discovering and organizing these invariants across different areas of knowledge.
So instead of just being good at chess or writing poems, AI would be good at understanding in a deeper sense.
Exactly. And when it comes to making AI more transparent and understandable to us humans, focusing on the invariants that the AI has learned and is using could provide really valuable insights. In cognitive science, it could lead to more accurate and predictive models of how human intelligence actually works, and that could influence future research in neuroscience and psychology. And even in a more philosophical sense, if we start thinking about knowledge itself as essentially the process of distilling invariance from our experiences, it could change how we view scientific discovery and the very nature of understanding.
Wow, that's a profound shift in perspective. Okay, let's dive a bit deeper into how these invariants show up in different areas. Earlier, we talked about prime numbers, and it seems like the gaps between them are totally unpredictable, just jumping around all over the place. But some of the things you sent suggest there's actually a kind of statistical invariance at play, even in that seeming randomness.
It does seem counterintuitive at first, right?
Yeah.
When you look at the sequence of prime numbers 2, 3, 5, 7, 11, and so on, the differences between them, those prime gaps do seem pretty erratic. But if you zoom out and look at the big picture, the overall distribution of primes, a really fascinating order starts to emerge.
So it's not about predicting the exact size of the next gap, but about seeing a pattern when you look at a huge collection of primes.
You got it. The prime number theorem, a cornerstone of number theory, tells us that on average, the gap between prime numbers around a certain number p is roughly equal to the natural logarithm of p. Now, this isn't an ironclad rule that applies to every single gap, but it describes the overall trend, and it becomes more and more accurate the bigger the prime numbers get. It's a bit like saying that while we can't predict where each individual raindrop will land, we can say something about the average rainfall in a region over a long period of time.
That makes sense. So the individual events might be random, but the overall behavior, the trend, is what's invariant. What about those Hardy-Littlewood conjectures? They dive into the distribution of specific types of prime gaps, right?
They go beyond just the average gap and make predictions about the frequency of specific patterns of prime gaps. Like twin primes, those pairs of primes that are only 2 apart, like 3 and 5 or 11 and 13. The conjectures suggest that while we can't pinpoint exactly where twin primes will pop up, their frequency over large stretches of numbers follows a remarkably stable distribution. It's like finding another layer of invariant structure within the seeming randomness of prime numbers.
And then there's this mind-blowing connection to the Riemann hypothesis and those eigenvalues of random matrices. That sounds like we're going down a deep, abstract, mathematical rabbit hole.
We are. The Riemann hypothesis, one of the biggest unsolved problems in math, is all about the distribution of prime numbers. And it turns out that the spacing of the zeros of this special function called the Riemann zeta function, which is closely related to prime numbers, statistically mirrors the spacing of the eigenvalues of large random matrices.
Okay, that already sounds complicated, but what does it actually mean?
It suggests this profound hidden connection between the seemingly deterministic world of prime numbers and the chaotic behavior of complex quantum systems. It's called the Montgomery-Odlyzko law, and it's like finding a secret passageway between two seemingly unrelated areas of math and physics. It hints at this deep underlying structure that might be governing both of them. And then there's the whole idea of self-similarity and scaling laws in the gaps between primes.
Self-similarity, like fractals, those shapes that look the same at different scales.
Exactly. Recent research suggests that there might be fractal-like patterns in the distribution of prime gaps. By analyzing the frequencies present in these gaps, researchers have found recurring patterns that persist across different scales of prime numbers. It suggests this quasi-invariant structure, where similar statistical patterns show up even when you're looking at primes that are vastly different in size. It's like the universe is whispering a secret code to us through the language of prime numbers.
It really is remarkable. So even though the individual gaps between prime numbers seem random and unpredictable, if you zoom out and look at the bigger picture, this whole meta pattern of statistical invariance emerges.
Exactly. Binary search is a great example because it shows how identifying and maintaining certain invariant properties is key to making sure an algorithm works correctly and efficiently. At each step of the search, there are a few things that absolutely have to stay true. These are the invariants. For instance, there's what we can call the search space invariant. It means that at every step, if your target number is actually in the original list, you can be absolutely certain that it's somewhere within the current section you're looking at. You never accidentally throw away the part of the list where your target might be hiding. Then there's the progress invariant. With every step, you're guaranteed to cut the size of your search area in half. This continual shrinking of the search space is why binary search is so efficient, especially for really long lists. It's like a detective systematically narrowing down the list of suspects. And lastly, there's the correctness invariant. This one ensures that you're always making the right choice when you decide to discard half the search space. Because the list is sorted, if the middle number you check is bigger than your target, you know for sure that your target can't be in the upper half, and vice versa. These invariants taken together are what guarantee that binary search will always lead you to the right answer, and it'll do it in the most efficient way possible.
It's fascinating how these underlying, unchanging principles are what make the algorithms so effective.
It's like the rules of the game have changed slightly, but the core logic, the invariant, still guides the search.
Okay.
And this idea of conserved quantities, things that stay the same, links back to Noether's theorem, that beautiful idea we talked about earlier, where symmetries and the laws of physics lead directly to these conserved quantities.
It's incredible how these invariant principles are baked into the fabric of the universe itself.
Exactly.
Invariants, those unchanging elements, are the bedrock, the scaffolding that holds everything together.
It's about seeing the common thread that runs through all these seemingly different areas. It's about recognizing that in the midst of all the change and transformation, there are certain fundamental properties that remain steadfast. And this preservation of something fundamental is what allows order to emerge from complexity, what provides the structure for understanding and knowledge. And as we discussed, the ability to identify and leverage these invariants seems to be deeply connected to intelligence itself.
And that brings us to the idea that true intelligence, whether it's the human brain or a sophisticated AI, is fundamentally about this ability to extract and utilize those invariant truths hidden within the vast sea of information that bombards us constantly.
It's not just about processing information. It's about finding the signal in the noise, the patterns that persist, the underlying structure that doesn't. Something that's key to understanding how anything, really, keeps its identity even as everything around it is changing.
Let's talk about similar matrices. Two matrices, say A and B, are similar if you can find an invertible matrix that makes this equation true. Think of similar matrices as the different ways of looking at the same underlying transformation, just from different perspectives. The cool part, they always have the exact same eigenvalue. The spectrum of a matrix, which is just the set of all its eigenvalues, is invariant. No matter what basis you choose, it stays put. It tells you something fundamental about the transformation itself.
It's really making me think, if different ways of looking at the same system lead us back to the same eigenvalues, what does that say about the true nature of the system itself?
It's a really thought-provoking question, right? Maybe these eigenvalues are telling us something deeper, something more intrinsic to the transformation, beyond just the way we happen to be looking at it. And to take it even further, let's think about Hermitian matrices for a sec. Those are matrices with a special kind of symmetry. And they always have real eigenvalues, and their eigenvectors, well, you can arrange those to form a beautiful perpendicular basis. And the best part is, even when you apply unitary transformations, think rotations and reflections in a complex space, that fundamental geometric structure doesn't change one bit.
So even when we're talking about these more abstract, complex transformations, there are still those core geometric relationships like the eigenvalues and the perpendicularity of the eigenvectors that are totally unshakable.
That's right. They provide an anchor, a solid foundation, even amidst all the change. The Schrödinger equation in quantum mechanics, that's an eigenvalue problem too, but it's for the Hamiltonian operator. The solutions, those are the energy eigenstates. They're eigenfunctions of H. And these energy eigenstates, they keep their functional form as time goes by. Their underlying probability distribution, it stays put.
So the most fundamental states of reality in the quantum world, the stable energy configurations, those are all represented by these invariant eigenfunctions of the Hamiltonian. That's incredible.
It is. They capture the unchanging aspects of a quantum system's energy.
It's really quite amazing.
It really is. We encourage you to take a look around in your own areas of interest and see if you can spot this principle of things staying the same, even as everything else is in flux. You might be surprised at how often this concept of invariance is actually at play.
Thanks for joining us on another deep dive. Until next time.